Hello everyone, welcome to Education in Hands. If we see in our last videos, we discussed about bolted connections and what are the different types of bolts and then its terminology in bolted connections and different types of failure modes. So today in this video, we are going to discuss about the design of bolted connections. First, if we see today's outcomes, we will see the notation of the bolt and then we will see the types of connections which we are using for design. In that one, we will discuss the bearing type of connections in today's video. If we see the notation of a bolt, according to Indian standards, it is given like grade 4.6. It is one kind of bolt where the 4 is representing the 4 into 100 times of its ultimate strength, where FUB equal to 4 into 100, that is 400 megapascals ultimate strength of bolt, and 0.6 is 400, which is ultimate strength, into 0.6 times, which is equal to the yield strength of the bolt, that is FYB, 400 into 0.6, which is equal to 240 megapascals. If we see another one is grade 8.8, where ultimate strength is FUB 8 into 100, 800 megapascals, and FYB or yield strength is equal to 800 into 0.8, that is 640 megapascals. So these two are mainly used grade of bolts. Likewise, we are having different grades of bolts which are given in the notation like grade 4.6, 5.6, 5.8, 8.8 likewise. So this is the notation of the bolt. After this, if we see the design of bolted connections, according to our Indian standards IS 800-2007, we are having two types of bolted connections, that is for ordinary black bolts and second is for high strength friction grip bolts, which is nothing but HSFG bolts. So the connection design for these two kinds of bolts will be carried out in two methods. First one is bearing type of connection and the second one is friction type connection for both lap joints and butt joints. So today in this video we will discuss about this bearing type of connection, which is the first type of connection given in clause 10.3 of IS 800-2007. So first, if we see what is meant by a bearing type of connection, means it is also called as slip type connection, where the slip between two plates which are connected together is allowed. See here, it is assumed like load to be transferred is larger than the frictional resistance caused by tightening the bolts. Means when two plates are connected together, right, we are connecting it with a bolt. So at that time, the load transferred on these two plates is larger than the frictional resistance. Means whenever these two plates are connected with a bolt, the holding capacity of the bolt is less when compared to the external load. Then next one is members slip a little over each other, placing the bolts in shear and bearing. So since it is a slip type connection, members will slip one over other. So with that, what will happen? The bolts will experience shear and bearing, which leads to the failure in shear and bearing. Then the number of bolts required for connection will be equal to the total load by strength of each bolt. So whatever the load acting externally on the connection by the strength of each bolt will give the total number of bolts required for a connection. Along with this, if we see here, a minimum of 2 or 3 bolts are provided even if one is enough for the connection. So if we calculate the total number of bolts required by total load by strength of each bolt, if it is coming around 1, means we will provide 2 or 3 to take care of the connection. if we see this connection, in this connection, the failure of a joint can be in bolt or in plate. So that strength of joint will be minimum of strength of bolt or strength of plate. So what it is saying here, the failure of a joint can be done in bolt or it may be in plate. So we need to take the strength of joint as the minimum of strength of bolt or strength of plate. So if we consider the strength of bolt is taken as the minimum of shearing strength of bolt, bearing strength of bolt and tensile strength of bolt, which are nothing but the failures we discussed in last video. So we need to consider these three conditions. Out of these three, the minimum will be taken as the strength of bolt, and then the strength of plate will be taken as the tensile strength of plate. So whatever the tensile strength of plate is exhibiting, we will take it as the strength of plate. And along with these four, we need to consider the effect of combined shear and tension. So out of these five, which are nothing but shearing strength of bolt VDSB, bearing strength of bolt VDPB, tensile strength of bolt TDB, tensile strength of plate TDN, and combined shear and tension effect. All these five we need to consider, and out of these five failure conditions, whichever is having least value is taken as the strength of the joint, that is nothing but VDB. So if we see, as per class 10.3.2, a bolt subjected to factored shear force VSB shall satisfy VSB equal to VDB. So the connection is safe, which is nothing but the factored shear force which is acting on the bolt will be equal to the design strength of the bolt, which is nothing but the minimum of these five conditions. So we will see how to calculate these five conditions one by one now. That is our design of bolted connection first of all. So the first one is shear capacity of the bolt. As per class 10.3.3, keep your book IS 800 along with you so that you can easily understand where these classes are available in the code book. So according to this class, what they mention is like the design strength of bolt VDSB as governed by the shear strength is given as VDSB equal to VNSB by gamma MB, where VNSB is nothing but nominal shear capacity of the bolt and gamma MB is the partial safety factor for bolted connection with bearing type of bolts. So here VNSB, V nominal shear capacity, how we are calculating means it is given by a formula in clause 10.3.3 as VNSB equal to Fu by root 3 into NN into ANB plus NS into ASB into beta LJ, beta LG, beta PK. So if we see the notation here, the first one Fu is nothing but ultimate tensile strength of bolt, and then NN and NS, if we see NN is number of shear planes with threads in plane. So if we connect two or three plates, the shear planes which are in place of thread section of a bolt, then those planes are taken in NN, and NS is number of shear planes without threads in plane. So if the threads are not in the plane, means only shank is there, then that section is taken as NS, and then ASB is the nominal plane shank area of the bolt, which is nothing but pi by 4 d square diameter of the bolt, and ANB is the net shear area of the bolt at threads. So whenever a bolt area is calculated at place of threads, its area is reduced, which is cross sectional area. That's why ANB is the net shear area of the bolt at threads, which is taken as 0.78 times of ASB. And the last one is beta LJ, beta LG and beta PK, which are nothing but the reduction factors. We are applying these reduction factors in different conditions. Where we will apply, let us see. The first one is beta LJ, which is nothing but the reduction factor for long joints. So as per clause 10.3.3.1, where we apply this reduction factor beta LJ. See, if the distance between first and last bolt in the joint measured in the direction of load exceeds 15D, then shear capacity VDB shall be reduced by beta LJ. So if the distance between first bolt and last bolt in the connection is exceeding 15D, which is D is nothing but diameter of the bolt, then if it is exceeding 15D means we need to apply this reduction factor beta LJ. So what is this beta LJ? It will be equal to 1.075 minus 0.05 LJ by D. So here D is the nominal diameter of the fastener and LJ is the distance between first and last bolt in the joint. And here we are also having a condition like beta LJ should not be less than 0.75 and it should not be greater than 1. It should be in between 0.75 to 1. Otherwise, we need to take the nearest values. Then next one is beta LG, which is nothing but reduction factor for large grip lengths. In clause 10.3.3.2 it is given. When grip length LG, which is nothing but the total thickness of the connected plates, either 3, 4, 5, how many plates are connected? The total thickness is nothing but the grip length. If it exceeds the 5 times diameter of the bolt 5D, then the design shear capacity shall be reduced by a factor beta LG. So in simple words, if we see here, LG, the total grip length, means the total number of plates connected. Its thickness is more than 5 into D, 5 times of diameter of bolt. Then beta LG reduction factor will be multiplied with this VNSB or VDSB. So what is this beta LG? Beta LG equal to 8D by 3D plus LG, where D is the diameter and LG is the grip length. And here also we are having two conditions. What are those two conditions? Means beta LG should be less than beta LJ, which means it should not exceed beta LJ. And one more is beta LG should not be greater than 8D. So if it is crossing more than 8D means we need to take the value of 8D itself. Likewise, then the third reduction factor is beta PK, reduction factor for packing plates, in clause 10.3.3.3. So here when we are adopting this beta PK, the design shear capacity of the bolts carrying shear through a packing plate exceeds 6 mm shall be decreased by factor PK. Okay, they gave something, but I didn't get it. So in simple words, if I want to explain means, I am taking this double cover butt joint connection. So here in this connection, if we see the two main plates are like blue plates. Two plates are connected using a double cover butt joint, but the thickness of plate 1 and plate 2 are different. So to maintain this connection equally, I am using a green color plate additionally, which is nothing but a packing plate. So here whenever we are using this kind of connection with the help of a packing plate, then the design shear capacity of bolts carrying shear through packing plates means we are using a packing plate to help the connection. So at that time, if this packing plate thickness exceeds 6 mm means, then we need to consider this beta PK reduction factor. So what is this beta PK? It will be equal to 1 minus 0.0125 TPK, where TPK is the thickness of the thicker packing plate. So if we are using two packing plates, we need to take the thickness of thicker packing plate, and if we are using only one packing plate like this, we will use the thickness of this packing plate. This is about the reduction factor for packing plates. Then if we see the second failure condition, that is bearing capacity of bolt, as per clause 10.3.4, it is given like the design bearing strength of bolt VDPB as governed by bearing is given as VDPB equal to VNPB by gamma MB. So here VNPB is nothing but nominal bearing strength of bolt, and gamma MB is the partial safety factor. So if we see how to calculate this VNPB, means it is given like 2.5 kb into D into T into Fu. So where kb is the smallest of E by 3D naught or P by 3D naught minus 0.25 or FUB by FU or 1.0. So we need to calculate these four, and then we need to choose the smallest one for the value of kb. So if we see what is this terminology means, here E is nothing but end distance of the fastener along bearing direction, which we discussed in our terminology, and then P is the pitch distance, then D naught is the diameter of the hole, FUB is the ultimate tensile stress of bolt, and FU is the ultimate tensile stress of plate or material, then D is the nominal diameter of the bolt, and then the T, which is nothing but summation of the thicknesses of the connected plates experiencing bearing stress in the same direction. Means the cover plates which we are using in the butt joint, we need to consider the thickness of both cover plates like this. So with the help of all these things, we will calculate the value of VNPB, and then we will calculate the value of VDPB, which is nothing but the bearing capacity of the bolt. Then here also there are some reductions in the bearing capacity of bolts. See here, the bearing resistance of the bolts in holes other than standard clearance may be reduced by multiplying VNPB with certain factors, which means if it is in standard clearance case, like if we see that table 19 for bolt holes, there we are having standard clearance, oversized, short slotted and long slotted holes. So at that time, if we are using oversized and short slotted holes, then VNPB value will be reduced with a factor 0.7, and if we are using long slotted holes, then it may be reduced with a value of 0.5. So these two need to be considered. If it is a standard clearance hole, then there is no reduction, it will be continued as it is. This is for bearing capacity of the bolt. Then if we see the third one, tension capacity of the bolt, as per clause 10.3.5, it is given like a bolt subjected to a factored tensile force TB shall satisfy TB less than TDB, where TDB is nothing but the design bolt capacity in tension. So TDB equal to TNB by gamma MB. So TNB is nothing but the nominal tensile capacity of the bolt, and gamma MB is the partial safety factor. So if we see how to calculate TNB, means it is given in clause 10.3.5 like TNB equal to 0.9 FUBAN, and it should be less than FYB into ASB into gamma MB by gamma M naught. So we need to satisfy this condition, otherwise we can take the value of 0.9 into FUB into AN. So here if we see the notation, FUB is the ultimate tensile stress of bolt, and FYB is the yield stress of bolt, AN is the net tensile area of the bolt, and ASB is the shank area of the bolt. Then gamma m naught, which we are using here, is partial safety factor against yield stress. This is for tension capacity of the bolt. Then the fourth one is tension capacity of the plate. It is given in clause 6.3.1. The design strength in tension of the plate TDN is given as 0.9 AN/FU by gamma M1. So if we see here, gamma M1 is the partial safety factor for failure at ultimate stress, and AN is the net effective area of the member, and Fu is the ultimate tensile stress of the material. So we need to calculate this TDN, which is for tension capacity of the plate. So we need to calculate this for the tension capacity of the plate. But here we don't know how to calculate the value of this AN. So for that, if we see here, the value of AN, which is nothing but net effective area of the member, will be calculated by using this formula, where AN equal to B minus ND naught into T for chain bolting, and AN equal to B minus ND naught plus sigma PSI square by 4GI into T for staggered bolting, where if we see the notation, it is given like B and T are like width and thickness of the plate, DH diameter of the hole, G gauge distance between the two bolt holes, and PS staggered pitch length between line of bolt holes, and N number of bolt holes in critical section, and I subscript for the summation of inclined legs which we are taking here. So this is for the calculation of net effective area. In problems we will see how to calculate this one. And the last one is the combined shear and tension as per clause 10.3.6. So if you see here, a bolt required to resist both design shear force, which is VSD, and design tensile force, that is TB, at the same time shall satisfy the condition like VSB by VDB whole square plus TB by TDB whole square, which should be less than or equal to 1.0. Then only we will take this consideration like combined shear and tension is safe in the design. So if you see these notations, VSB is the factored shear force acting on the bolt, VDB design shear force or design shear capacity, then TB factored tensile force acting on the bolt, and TDB design tension capacity. So out of these 5 failure conditions, we will select the least value and we will choose that least value as the design strength of the bolted connection. So this is the design of a bolted connection. In next video, we will see the strength and efficiency of the joint. See you in the next video. Thank you.